Hello students, in today's lecture we are going to see the rules for writing the electronic configuration. This is very important in understanding why do we follow certain orders in while we are writing the electronic configuration of any element. And this topic is also important from competitive exams point of view. Many times, almost every year, the competitive exams will be asking the questions based on this concept. Like NSEJS will also be asking the question. Even IIT or NEET, they will be asking the questions based on this concept. So let's get aware with this concept. What is this concept? So, what are the rules which should be followed while you are writing the electronic configuration? The first rule is Aufbau's principle. Now, what is this Aufbau's principle? This says that subshell with lower energy will be filled up first, or we can say that subshells are filled in increasing order of energy. That means you will be filling the lower energy subshells first, then only you will be filling the higher energy subshells. So for example, let's take an example. Suppose that A, B, C and D are four subshells. We have four subshells over here. Suppose that energy of A is greater than energy of B is greater than energy of C, and the D is having the lowest energy, right? So according to the Aufbau's principle, the first subshell that you're going to fill should be D. The subshells will be filled up in increasing order of energy. That means the lowest energy subshell will be filled up first. So if I write the order of filling these subshells, will be D will be filled up first, then you will fill C to its maximum capacity, then you will fill B, then you will fill A. Right? Now question is, how do you decide the energy order of the subshells? So for energy order of the subshells, we follow N plus L rule. N plus L rule, this helps to decide energy order of different subshells. Right? So N plus L rule will help us to decide the energy order of different subshells, or simply to compare the energies. Of two subshells, two or more subshells. Right. Now let's try to understand what is this N plus L rule. So in N plus L rule, this N is principal quantum number, while L is azimuthal quantum number that we have seen in the previous lecture of the same series. Azimuthal quantum number. Right. Now, how does this decide the energy? So remember that N plus L, the sum, is directly proportional to the energy of subshell. This value, the value N plus L, is directly proportional to the energy of the subshell. That subshell which has more value of N plus L will have more energy. The one which has lower sum of N plus L will have lower energy. Let's try to understand this. For example, 1s is a subshell, we know that from the previous lecture. 2s is also a subshell, 2p is also a subshell. Let's try to compare their energies. So if you find N for the 1s, is it 1? The principal quantum number is 1 over here, because 1s, as this number denotes, this denotes the principal quantum number, we know that. And S, for S subshell, the value of L is 0. If you take N plus L, the N plus L is 1. For 2s, the value of n is 2 and the value of L is 0 again because it's S subshell. The n plus L value will be 2. For 2p, the value of n is 2 but value of L is 1. If you take the n plus L value, we get 3. So what do we see over here is that n plus L of 1s, n plus L of 2s and L plus L of 2p. You will see that n plus L value of 2p is maximum and 1s is minimum. So this is the order of n plus L value for the. So same will be the order of energy also because n plus L value sum is directly proportional to the energy of the subshell. So we'll say that if E1s is the energy of the 1s subshell, E2s is the energy of 2s subshell and E2p is the energy of 2p subshell, then energy order will be this. So in what order we should fill them? According to the of-watch principle, it should be filled in increasing order of energy. That means order of filling them, filling the electrons will be in this order. First you will fill 1s. The maximum number of electrons that S subshell can take is 2. We know that. So the number over here above the subshell is the number of electrons, right? So we'll fill 1s to its capacity. Now the next electron will move to the next subshell. 1s is already full, right? Now the next electron will go to 2s. We'll fill 2s to its capacity with the 2 electron. Now the next electron will go to 2p and we can fill it maximum of 6 electrons. So this is the order of filling of the subshells, right? 1s will be filled up first, then we'll fill 2s, then 2p, then next higher energy subshells. Fine. In many cases, you will find that the two subshells have the same value of n plus L, right? In case two subshells have same value of n plus L. In that case, how will you decide the energy? So in that case, n plus L value, when it's same for two subshells, in that case, the energy will be decided based on the value of principal quantum number, which is n. In that case, n will be directly proportional to the energy. The one which has higher value of n will have the higher energy. The one which has the lower energy of n will have the lower energy. For example, if you compare 3D and 4s, let's compare 3D and 4s in terms of energy. So for 3D, the value of n is 3, right? And sorry, my mistake, my bad over here. Let's take 3p and 4s, 3p and 4s, right? So if you check 4s, the value of n is 4 and L is 0. So n plus L value will be 4 plus 0, 4. For 3p, the value of n is 3 and value of L is 1. The n plus L value is 4. We see that 3p and 4s both have same value of n plus L. In such cases, we'll decide the energy based on the value of n. The one which has higher energy of n will have the higher energy. So in these two cases, 4s has the higher value of n. That is why energy of 4s will be greater than energy of 3p. So obviously you will fill 3p first, then only you will fill 4s. Right. So if you write, first shell has 1s, one subshell only 1s. Second shell has 2s and 2p. Third shell has 3s, 3p and 3d. Fourth shell has 4s, 4p, 4d and 4f. Likewise, right? Fifth shell will have 5s, 5p, 5d, 5f in the similar way. Let's try to arrange them in terms of energy, in energy order. So for n plus L value of this 1s, should it be 1 plus 0 equals to 1? The value of n is 1 and the value of L is 0, n plus L value, right? For 2s, the value of n is 2, the value of L is 0, so 2. For 2p, it should be 2 plus 1 equals to 3 because the value of n is 2 and L is 1. For 3s, 3 is the n and 0 is the L, so sum is 3. For 3p, 3 is N and 1 is L, so N plus L is 4. For 3D, 3 is N and 2 is L for D subshell, so it's 5. For 4S, 4 plus 0 equals to 4. 4P, N is 4, L is 1, so 5. 4D, 4 is N and D is 2, so it's 6. For 4F, 4 plus 3 equals to 7. Let's arrange them in energy order. We see that 1s has the lowest N plus L value. We can see that. So 1s will be filled up first, right? Then 2s, then 2p. Because if you compare 2p and 3s, both of them have same value of N plus L, but 2p has lower value of N, that is why it has lower energy than 3s. Then we fill 3p. We see that 3p and 4s has the same value of N plus L, but 3p has lower value of N, that is why 3p has lower energy. But after 3p, we have to take 4s. Why? Because 4s has lower value of N plus L. There is no argument in whenever there is a different value of N plus L for two different subshells, the lower value of N plus L will have the lower energy. So if you compare 4s and 3D, 4s has lower value of N plus L, that is why 4 is before 3D. After that, we have two subshells, 3D and 4p. Both of them have same value of N plus L. So 3D will have the lower energy than 4p because 4p has N equals to 4, which is higher than 3D. Now, after 3D, it's 4p, 4D and 4f. Of course, between them, fifth shell will also come. You can practice that yourself. You can write all the subshells, 5s, 5p, 5d, 5f, then 6x, 6p, 6d, 6f. You can practice that and you can find N plus L for all and then arrange them according to the N plus L value, according to the energy order. Okay, this is the energy order. If you go from left to right, from 1s till 4f, we see that energy is increasing, right? So this is the increasing order energy, right? Increasing order energy of these subshells. So same will be the order of filling of electrons. So first we'll fill 1s to its capacity, then we'll move to 2s, we'll fill 2s to its maximum capacity, then next higher energy subshell 2p, fill it to the maximum capacity, then 3s, then 3p, then 4s. Just follow this order, right? So this was Aufbau's principle. Next, second one is Hund's rule of maximum multiplicity. What does this say? This deals with degenerate orbitals. Now, what is the degenerate orbitals? So, by definition, the degenerate orbitals are those orbitals having same energy. Those orbitals which have the same energies are called degenerate orbitals. For example, we know that p subshell, any p subshell, whether it be 2p or 3p or 4p, any p subshell has 3 p orbitals. We know that from the previous lecture. Any p orbital has p subshell has 3 p orbitals. Okay, all these 3 p orbitals of any p subshell will have the same energy and we'll call them degenerate orbitals. In the similar way, any d orbitals, any d subshell, whether it be 3d, 4d, 5d, any d subshell, we know that the d subshell has 5 d orbitals. Now, all the 5 d orbitals of any shell, of a particular shell, all the d orbitals will have the equal energies and so they are degenerate orbitals, right? So similar way, F subshell, any F subshell you take of any shell of a particular shell, all the F orbitals, there are 7 F orbitals, we know that. All the 7 F orbitals of the given shell will have the same energy, so they are also degenerate orbitals. For example, if I take 2p, 2p is a subshell, it's a p subshell of second shell, right? Now, this p subshell of second shell has 3 p orbitals, we know that. All these 3 p orbitals of second shell will have the same energy, or they are degenerate orbitals. Fine. But you will not say 2p and 3p, all the p orbitals over here are degenerate. No. Why? Because you can simply check using the n plus l also. If you check n plus l for this, is it 2 plus 1 equals to 3? And for this n plus l value is 3 plus 1 equals to 4. This is quite obvious to us that the 2p has lower energy than 3p, right? But all the p orbitals in the third shell will have the same energy. They are degenerate orbitals. All the p orbitals in the second shell are degenerate orbitals. Similarly, 4p, all the p orbitals of the fourth shell are degenerate orbitals. You cannot say that all the p orbitals of fourth shell and 3 shell are degenerate. No, that's a clear-cut no, right? Because using n plus l, you can clearly see that 2p and 3p, these two subshells have different energies, right? Same goes for the 3d, 4d, 5d, and 6d and 7d, like that. This is the energy order, right? But all the d subshell, all the d orbitals of the third shell are degenerate, or the d orbitals of the fourth shell are also degenerate, all the d orbitals of fifth shell are degenerate. Same goes for the f subshell, right? Now, what does the Hund's rule deal with degenerate orbitals? So, remember that in case of degenerate orbitals, electrons occupy them singly, then only pairing starts. Let's try to understand this statement very carefully. Right. Now, we have seen that how do we represent orbital representations. We have seen in the previous lecture that how do we represent the orbitals. So we use the square diagram to represent the orbitals. So for example, 1s will be shown as 1 square, 2s will be shown as 1 square, because s subshell has one orbital only. 1 square represents one orbital. 2p will have 3 orbitals, so this can be divided into 3 squares. This is one of the p orbital, another p orbital, another p orbital, right? Same way, 3s will have just one, like that. Now, so according to this, when you are filling the 2p subshell, for example, when you are filling 2p subshell, right? So suppose that we have to arrange 8 electrons. Suppose we have to arrange 8 electrons. Fine. If we are arranging 8 electrons from the off-watch principle, do we have this order? 1s, 2s, 2p, 3s, 3p, 4s, 3d. We have seen that in the off-watch principle. We got this energy order, and same is the order for the filling of the electrons also. Fine. Now, if you remember the spin quantum number, the first electron goes, if it goes with the clockwise spin, the another electron goes with the anti-clockwise spin. Fine. Now, 1s is full. 1s is full with 2 electrons. Fine. Now, we'll move to the 2s. 2s will have the 2 electrons again with the opposite spins. So, 2 electrons over here. Now, in the 2p, we have 3 orbitals over here. How are we going to fill them? So, according to the Hund's rule, we will fill them singly first. So, till this point, we had arranged 4 electrons. So, this is the 5th electron, 6th electron, 7th electron, and this is the 8th electron, right? This is the 8th electron. This is what Hund's rule states, right? So the configuration becomes p hash 2p hash 4 electrons. We can see that. So 1s2 2s2 2p4. We'll take one more example. Suppose that we are to arrange 26 electrons. Let's try to arrange 26 electrons, right? So we have this order from the Offwatch principle. We have this order. Right, this is the order we have. Let's take the orbital diagram. This is 1s, 1 square bracket, 2s square bracket, 2p, 3 squares, 3s, 1 square, 3p again 3, because p has 3 orbitals, 4s again 1, but 3d has 5 orbitals, so 5 squares over there. Let's try to fill the 26 electrons in these. So 1s can take maximum of 2 electrons with the opposite spins. Fine. Then we'll move to 2s. We arranged 4 electrons, 22 more electrons to arrange. 2p will have this electron, 5th, 6th, 7th, then 8th, 9th, and 10th electrons, right? According to the Hund's rule. So 10 electrons are arranged. Now in 3s, again it will take 2 electrons, right? Now 3p, once again we have arranged 12 electrons so far. Now the 13th electron is here, 14th electron, 15th electron. First they occupy the degenerate orbitals singly, then the pairing up starts, right? Now we have arranged 18 electrons so far. If you check, we are left with how many electrons more? We are left with 8 more electrons to arrange, right? Now 4s will have these electrons. There is no confusion in 4s, but in 3d again we are left with 6 more electrons, right? So this is, till this point we have arranged 20 electrons. So 21st electron goes here, 22nd, 23rd, 24th, 25th. This is 26th electron. So we see the Hund's rule of maximum multiplicity. This is Hund's rule over here. Here also we have applied Hund's rule. Here also we have applied the Hund's rule. Remember, Hund's rule is very important. They will be asking the questions based on this concept, right? I will give you a question. We all understood that how do we apply the Hund's rule. It is applied in case of degenerate orbitals. Fine. So there was a question asked like this: which one represent correct electronic configuration of nitrogen 7? Now nitrogen 7 has 7 electrons, we know that, right? So the options were given like this: 1s, 2s, 2p, b, 1s, 2s, 2p, c, again 1s, 2s, 2p, and the option D, again 1s, 2s, and 2p. Now it was given like this: now, if we see which one of them follow the Hund's rule properly, right? So this one doesn't follow the Hund's rule, right? We have not given single electrons. The electrons have not occupied the degenerate orbitals singly first, right? So 2p does not apply the Hund's rule. That's wrong, right? B also doesn't right? Why? Because this third electron should have gone here. Okay. C also doesn't apply, although they have occupied them singly. But remember that one more thing I missed to say that time. Remember one more thing is that according to the Hund's rule, you have already known that electrons occupy the degenerate orbitals singly first, then only the pairing up starts. We have already seen this statement. There is one more statement which is in the same rule, is that all electrons occupying degenerate orbitals singly comes with parallel spin. All the electrons which are occupying the degenerate orbitals singly must come with the parallel spins. Or if the first electron is clockwise spin, all the two electrons should also come with the clockwise spin only. If the first electron is anti-clockwise spin, all the two electrons over here should come with the anti-clockwise spin only, right? So this one is correct. This one is correct because this follows the Hund's rule properly. The electrons have occupied the orbitals singly. First statement is satisfied. Also, all the electrons are there with the same spin. Second statement satisfied. So this one is the correct electronic configuration of nitrogen, right? Okay, there is one more possibility for the nitrogen. 1s, 2s and 2p, right? So 1s, 2 electrons, 2s, 2 electrons. There is no confusion at all in 1s and 2s. But in the 2p, electrons should occupy them, the degenerate orbital, singly with the parallel spin. If we see, the first electron was with the anti-clockwise spin. That's why other two are also with the same spin, anti-clockwise spin. So this one is also correct, right? So this was Hund's rule of maximum multiplicity. What did we learn over here? That in case of degenerate orbitals, electrons will occupy the orbitals singly first. The pairing will start only when the electrons has occupied the degenerate orbital singly. That too, all the electrons in the degenerate orbitals must come with the parallel spin. If the first electron you took with the anti-clockwise spin, all other electrons in the degenerate orbitals should be in the anti-clockwise spin only, right? Or if you are taking with the clockwise spin, the other electrons which are occupying singly those degenerate orbitals should come with the clockwise spin only. So that was Hund's rule. The next rule, which is also important, is Pauli exclusion principle. According to this, no two electrons in an atom can have same set of all four quantum numbers. At least one of the quantum number must be different. Let's try to understand this. Right. Now, first thing is that if I write 1s over here, right, what will be the set of quantum numbers for 1s? If suppose there is this electron with a clockwise spin, right? So the value of n will be 1, value of L will be 0, we know that. Okay, value of m for the s subshell is just 1, 0. Now s will be plus half. For clockwise spin, we always take the spin quantum number as plus half, right, by convention. So this is the set of quantum numbers for the first electron in 1s. What will you write? How will you write? Will you write as 1, 0, 0, half? You write in this order, N, L, M, S. Principal quantum number, then the azimuthal quantum number, then magnetic quantum number, then spin quantum number. This is a set, right? If you had to write the set of quantum numbers for the second electron, will you write n equals to 1? And since the second electron is in the s subshell only, s or orbital only, so L equals to 0. Value of m is 0 for s subshell, we know that. But s is minus half. So for the second electron, is this the the set 1, 0, 0, minus half? Right? So this is how you find the set of the quantum numbers. Okay. Remember, in case of p subshells, for p subshells, the value of L is 1. So the value of m is minus 1, 0, and plus 1. Right? By convention, we start from here. This orbital has minus 1 value, 0 value, plus 1 value. These values are the values of m. Right? So if the electron is there in this orbital, we'll say the value of m over here there is minus 1. If the electron is in this orbital, we'll say that the value of m is 0. In this orbital, value of m is plus 1. Similarly, we can write for the d subshell also. So d orbitals are like this, 5, right? For d, the value of L is 2, so value of m should be minus 2, minus 1, 0, plus 1, plus 2, right? So you start from here, from the left hand side, minus 2, minus 1, 0, plus 1, plus 2. So if the electron is there in the first orbital of d, we'll say the value of m there is minus 2. If in this, value of m is minus 1. Similarly, value of m 0, 1, 2. Same goes for the F subshell also. F subshell has 7 orbitals, we know that. Right. So F, the value of L is 3. So value of M is minus 3, minus 2, minus 1, 0, 1, 2, 3. We know that. Right. So this one, the electron in this will have a value of minus 3. This one will have minus 2, minus 1, 0, 1, 2, and 3. This is how you find the values of M. Right. So let's try to understand the Pauli exclusion principle, right? So suppose that I write the electronic configuration of nitrogen, for example, 7. Right. So 7, this is the order you need to follow. Correct? This is the order we need to follow according to the Aufwärts principle, right? We have to arrange 7 electrons. We see here that atomic number is 7 and nitrogen is neutral, so the number of electrons is also 7. So let's arrange 7 electrons. So if you write the electronic configuration, this should be the electronic configuration, right? Now let's try to find out the set of quantum numbers for each electron over there. So 1s is this, first electron, second electron, 2s, first, second electron, 2p. 2p has 3 electrons, we know that. These 3 electrons, we have arranged 7 electrons, right? So for the first electron, set of quantum numbers, let's find the set of quantum numbers. First electron, this is the first electron, right? It is in the first shell, so value of n is 1. It is in the s subshell, so value of L is 0. For s subshell, the value of m is also 0, s orbital, right? Now, first electron is with the clockwise spin, that is why the value of s is plus half. Fine. For second electron, which is this is the second electron. It is in the first shell, 1, value of n is 1, s subshell, L is 0, s orbital, 0, but it is with the opposite spin, so minus half. Right. Now, for the third electron, which is this is the third electron, right? So third electron is in the second shell, so n is 2, s subshell, L is 0, s orbital, m is 0, but with the clockwise spin, so plus half. Fourth electron, this is fourth electron. So for this second shell, s subshell, s orbital, anti-clockwise spin, minus half. This is fifth electron. So for fifth electron, it is in the second shell, so 2. In the p subshell, that's why 1. Right now, I have told you in the previous page, value of m will be like this, minus 1, 0, plus 1. Because L is 1, m will be minus 1, 0, plus 1, right? So we'll start from the left. So value of m for the fifth electron is -1. It is with the clockwise spin, so plus half. For 6 electrons, it should be 2, 1, 0 and plus half. 7th electron, it should be 2, 1, 0, sorry, plus 1, not 0, plus 1 and plus half. If you check these 7 electrons, you find at least one of the quantum number is different, right? So that is the statement of the Pauli exclusion principle. It says that no two electrons in an atom can have same set of all 4 quantum numbers, right? So similarly, if you write the electronic configuration for any element, any atom, you will find two different set of quantum numbers for two different electrons. Okay, so these three are the rules which governs how do you write the electronic configuration, right? Okay, to remember these orders 1s, 2s, 2p, 3p, we have a shorthand tool, we have a table. So for now you can refer the table. You can always draw this table. 1s, second shell has 2s and 2p, third shell has 3s, 3p, 3d, fourth shell has 4s, 4p, 4d and 4f, fifth shell has 5s, 5p, 5d and 5f, 6s, 6p, 6d and 6f, 7s, 7p, 7d and 7f. Now you start drawing the arrow from here. 1s, then 2s, then 2p, then 3s, then 3p, then 4s, then 3d, 4p, then 5s. Then you similarly go like this. Just intersect them diagonally, right? So this is the order. You start from this end of the arrow. You start filling in this order only. You start from here, this end. You start from here. You start filling all the subshells coming in the way, right? This should be the order. This is according to the n plus l rule only. You should refer to the table for some time only, but you should practice it so many times that you remember the order, right? You cannot refer to the table all the time. That will consume a lot of time. So for practice, you can refer to the table. After then, gradually you can practice the electronic configuration for more than 5 times, 10 times. You will automatically remember the order that 1s should come first, then 2s should come, then 2p, then 3s, then 3p, then 4s, like that. So let's see how do we fill. So suppose that I have to write the electronic configuration of calcium. Atomic number is 20. So electronic configuration is the arrangement of the electrons, how electrons are arranged in an atom, the address of the electron, as we have seen in the previous lecture, right? So 20 electrons, how the 20 electrons are arranged, we'll see. We will always start from this end, right? So fill 1s to its capacity. We know S subshell can take maximum of 2 electrons, so 1s 2. Now, if you go along the arrow, you find there is 2s. So fill 2s. Again, S can take maximum of 2 electrons. The electrons over here that you see the number, these numbers are number of electrons. Fine. After 2s is full, you'll go to 2p. See, if you follow this, you'll go to 2p. Fill 2p. 2p can take maximum of 6 electrons. So we gave 6 electrons to 2p. Now, after 2p is full, you'll go to 3s. Fill 3s with 2 electrons. After 3s, you will fill 3p, 6. We have arranged 18 electrons so far. If you count 2 plus 2, 4 plus 6, 10, 12 plus 6, 18. We are left with 2 more electrons, right? So after 3p, you should go to 4s, not to 3d, right? You will go to 4s. We can see according to this, and we have also seen the Watch principle that 3d has higher energy than 4s. That is why we fill 4s first. So this is called the electronic configuration of calcium. Let's take one more example. Let's try to write the electronic configuration of manganese, 25, right? So we have to arrange 25 electrons this time. So start with 1s, 1s 2. After 1s, we'll fill 2s, 2s 2, 2p 6, then 3s 2. After 3s, 3p, 3p 6. After 3p, we'll go to 4s, 4s 2, then 3d, 3d5. So this is how you write the electronic configuration. For practice, you can write the electronic configuration from atomic number 1 till atomic number 30 for practice, right? And you can repeat it as many times as possible. This is very important. You must have this knowledge of writing the electronic configuration, right? So in the next lecture, we will be dealing with the application of electronic configuration. Where do we use electronic configuration? So we will see that it's quite interesting. The significance of electronic configuration is very, very interesting. So that we will be seeing in the next video lecture.